We will come back at the end to look at more information demand from our system models for adaptation and mitigation. But for just initial discussions, we will use this schematic of geoengineering methods, which range from solar radiation management, like putting reflective aerosols in the upper atmosphere, mimicking volcanoes, which we saw actually can have global cooling effects, but we don't necessarily know all the unintended consequences coming out of that. But we know that just reflecting solar radiation will cool, but it doesn't remove CO2 from the system. So ocean acidification and other health issues, crop yield losses, and many other sea level rise, etc., can go on if we don't do something about emissions. So this can at best be a temporary or a solution as a part of the package that deals with other issues like decarbonization. There are also ideas on cloud seeding, which would increase reflectivity of the clouds and create higher albedo, which would have different consequences than the reflective aerosols. And space mirrors is another idea that is being discussed. So it seems like it's pretty much clear that at some point some sort of a solar engineering idea will be tried, other than of course forestation, which is happening naturally and intentionally, along with the deforestation that we just looked at in the Earth system trends. CO2 capture from the air plus storage, what is called CCS, is already happening. It's a matter of scales. And from fossil fuels themselves at source is considered somewhat easier, but the question always is it still carbon neutral, and how much does it cost? How many dollars or some other currency per ton is affordable in terms of capturing CO2, whether it's from air or from fossil fuel burning at power plants or whatever? And what is the scale? How many tons do they sequester in a year compared to, let's say, the global warming targets we set, like 1.5 degrees or 2.5 degrees with a certain probability by 2100? Or let's say we become brave and move it closer to 2050. So look at the trajectories we are on and see what withdrawal will be needed. Ocean fertilization, we mentioned a little bit in the other course, where you have regions in the ocean which are called HNLC regions, high nitrate, low chlorophyll, because nitrate that is upwelled by the ocean processes is not being utilized for photosynthesis, which means not enough CO2 is being sequestered by the marine ecosystem, because the ecosystem is limited by micronutrients like iron. So you go and dump a bunch of iron in the ocean and see if you can enhance phytoplankton productivity and CO2 drawdown. There is some success in this idea, but what needs to happen? Once you dump iron, the additional CO2 that's captured has to be drawn down to the bottom and sequestered away. That's not clear that that's what necessarily happens, that a lot of the stuff gets, a lot of the primary production gets recycled, which means it re-releases the CO2, additional CO2 that it took down. And in the process, it may even end up driving heterotrophic respiration and reduce oxygen. So scalability and actually long-term application of this method is also doubtful. So in general, these all amount to CO2 removal. In the solar geoengineering, there are 6 proposed methods, as we said already. Send a giant mirror into orbit around 400 kilometers, release reflective aerosols into the stratosphere about 20 kilometers up, and you have releasing micro bubbles to make the ocean surface more reflective, so just increase the albedo in the ocean itself, and you use ships to do other things like spray sea salt from a ship to make clouds brighter, so more reflective, and shinier crops and buildings reflecting, so increasing albedos in various way. Cloud thinning, so remove cirrus clouds which have a net warming effect. So the high thin clouds called cirrus clouds allow shortwave to come in and trap outgoing long wave. So if you can reduce them, of course you have to know what role they play in the overall system as well. And this is an anchored sprayer of, I cannot even read the captions here, but you get a sense. But Earth system models also need to serve process understanding, because we need to understand paleoclimate and climate sensitivity and the past analogs, potential analogs for global warming, going all the way back. So you have many models which have looked at reconstructing pieces of historic paleoclimate reconstruction. So this is showing various examples of the Devonian, Carboniferous, Permian, Triassic. I hope I have the periods right, Jurassic and Cretaceous. So these are Oligocene, Miocene, much closer to now. Pliocene, Pleistocene, getting into hominids, our ancestors, and of course the millennial timescales and so on, reconstructing various paleo evidences like the ice cores and so on. Okay, so process understanding should also be part of the role of an ESM, but again, if you want to make a simulation that is all the way long, you will make many compromises on the details of the ESM, because just the computational power required just is impossible at this time to run on these millions of year timescales. That's why people just use simplified models for million-year timescales, thousand-year timescales, millennial, thousands of year timescales, and so on. So this is the role of the models that are demanding Earth system models with various details. The whole thing started, of course, by representing the Earth in terms of boxes, what we call grids. So this is showing the atmosphere, but you have similar things for the ocean. And when we say resolution, this is what we mean. What is the dimension of the side here? So let's say you're trying to represent clouds and rain here, and if the model has order 100-kilometer grid box on the side, then you have to make sure that processes like clouds, which are very small, you can always look out and see there are tiny clouds floating around, but there are also big clouds which are convective clouds. So the process that you want to capture is very critical for deciding the time scale and the spatial scale of the model's ability, as we will see further on. So the 3D grid box then wants to do momentum, energy, thermodynamics, moisture dynamics, greenhouse gas effects, aerosol effects, which we talked about in terms of direct and indirect effects. So direct effect on radiation scattering and absorbing, indirect effects on processes of condensation nuclei, cloud formation, cloud properties, cloud brightness, etc. And water vapor dynamics, which happens from molecular scale to cloud scale. So it's a tedious, very complicated, very complex process, and we don't necessarily understand all the processes like moisture dynamics from molecular scale to cloud scale. We will see what that means in terms of uncertainties. And these are not something that can be solved analytically. You need computers, which means the cost of computing and just the time scale it would take to run the model for the time scale you are trying to resolve will be not so easy. So there is a quick rendition of the processes going from seconds to minutes to processes on hours, days, frontline squalls, tropical cyclones, all the way to climate variations with going through natural modes of variability like El Nino and La Nina, and you have a similar process range of processes in the ocean going from millimeters and seconds to hundreds of years and tens of thousands of kilometers. Obviously, in climate change, ocean is a critical player because that's the one that has the ability to give us these very low frequency time scales by storing heat and releasing it on various time scales. Remember this global conveyor belt we saw, which has hundreds to thousands of year time scales. And then you have glaciers which interact with the ocean in terms of locking up water from the ocean on land and re-releasing it, changing sea level, changing shelf areas, changing productivity, changing carbon sequestration, carbon cycle, methane cycle, nitrogen cycle, and so on. So obviously we have to see which models are trying to do what, but as we saw early on, you have a range of options, and variable dynamic modeling approach imagines that you can choose the processes, timescales, resolutions, and so on, and try to pick the best model. Is it always possible? We'll see some examples.